Okay, so today we're going to finish up 6.1, and then we'll take a look at 6.2, part of 6.2. All right, so first thing we're going to look at in 6.1 is called arc length. And the last thing we're going to look at is angular velocity. So those are the two things we're going to finish up first. All right, so let's take a look at a picture. And I'm going to show you what we're going to try to do. So let's say we draw a circle. And we put an angle in the circle. I'm going to make it 90, but it could be any size angle you want. Arc length is the length between this point and this point measured along the circle. That's what we're going to find. And the length of this arc depends on two things. First, it depends on how big of a circle do you have, and it depends on how big the angle is in that circle. Okay, so it depends on two things. Now, let me draw another circle. And assume they're the same size. Okay, how big is the angle on the left? Yeah? Okay, so this is a picture of a 90-degree angle. Now I'm going to draw a picture of 180. The initial side. Here's the terminal side. And here's the arc for 180. So this one is 180. How does the size of the angle in picture 2 compare with the size of the angle in picture 1? Yeah.
It's twice the angle.
Yeah, it's twice as big. So the angle in picture 2 is twice as big as the angle in picture 1. Now I have the same question again, but I want you to look at the arc. How does the length of the arc in picture 2 compare to the length of the arc in picture 1? Yeah? It's also twice as big. And that's important. So the key here is that the angle size and the arc size are what we call directly proportional. If you have the same size circles, and you double the size of your angle in the circle, then you would also be doubling the size of your arc. If you made your angle half as big, you would be making your arc half as big. So angle size and arc size are directly proportional. Any question on that? And because they are directly proportional, that allows us to set up a proportion. Not everything is directly proportional. For example, if you increase one thing, the other thing doesn't always increase. For example, the amount of time you spend studying and the grade you get on a test, it is not directly proportional. It is not a guarantee that if you spend twice as long studying, you're going to do twice as well on the test. No, it's not a guarantee. But this is directly proportional. So we had a fact yesterday about angle size and about angle size. Does anybody remember? If I draw this circle and make an angle here, that's exactly 1 radian. The length of this arc is the same as something else in the picture. Does anybody remember if this angle is 1 radian, what this arc is the same as? Yeah?
It's the same as, I don't know what you would call it, but like, I guess the sides of the angle, like the terminal side and initial sides.
Yeah, that would be the radius.
Yeah.
So that's a special fact that's true if you draw an angle of 1 radian. The arc size and the radius size are equal. We can use that special fact to come up with a formula. That special fact is kind of like saying in 1 foot there's 12 inches. That is a special fact about feet and inches. Once you have that, you can convert anything you want between feet and inches. You just need to start with something. You could start with in 2 feet there's 24 inches. That's a true fact as well. But you need something true. And this is what we're going to use that's true for us. If the angle is 1 radian, then the arc size, the arc length and the radius length are equal. So remember that these two things are equal. All right, here's a circle. And I've drawn 2 angles in the circle. One angle I've called theta. The other angle is theta 1. And then the arcs that correspond to those angles, that's an S, and that's an S1. So I have 4 things labeled in that picture. 2 angles, 2 arcs. The reason I labeled 4 things is because I'm trying to set up something like this. I'm trying to set up a proportion where one side is going to be a fact that I know is true. And on the other side is going to be some information that I want to figure out. But I need to get one side to be information that I know is true. Okay, so let's set up a proportion with these 4 things. And hopefully we can get one side to be something we know is true. Now, when you set up the proportion, you can do it lots of different ways. You just have to make sure that however you set it up on the left, if you do inches in the top and feet in the bottom, you need to do inches in the top and feet in the bottom on the right. Now, we're not doing inches and feet. We're going to do angle size and arc size. Angles and arcs. That's what we're going to do. So let me set up the left side, and then I'll see if somebody else can set up the right side. Let's do angle over arc. So I compared the angle 1 to arc 1. And to keep the pattern similar, does anybody have an idea what I would put on the right? Mark?
Angle, well, whatever that character is over S.
Theta.
Theta over S.
Theta over S, yeah. Again, if you're saying, wait, why can you set up a proportion like that? Because arc size and angle size are proportional. If you make one twice as big, you make the other twice as big. That's why you can set up something like this. Right. Now, on the left-hand side, this is where we usually fill in a true statement. So we need to pick numbers. 1 foot, 12 inches. We need some numbers there. Well, let's suppose that our angle was 1 radian. Then that automatically makes the arc, what did we just say? The arc is, if the angle is 1 radian, then the arc is the same size as the radius, which will be given to you in the problem. All right. There we go. So this right here, what I just circled, that's like our 1 foot equals 12 inches. That's our starting fact that we're going to use. So if the angle is 1 radian, then the arc is automatically the same size as the radius, which will be given to you in the problem. Now, the other side, those are our question marks. That's what we don't know. Those would be things we'd have to figure out. And does anybody remember, how do you solve a proportion? Somebody said this term earlier when we were going over the homework. Yep. You cross multiply. So you do S times 1. And you get S. And then you do R times theta. And you get r times theta. And that is called the arc length formula. So one thing that's important to notice about the arc length formula is that it only works in radians. So the angle in this formula has to be in radians. So the formula is S equals R times theta. S is your arc length, R is the radius of the circle, and theta is the angle in radians. And the way it works is you will always be given 2 out of 3 of the letters in that formula, and then you have to solve for the third one. So here's a problem where they've given you the problem 2 ways. They're going to give you a picture, and they're going to give you a sentence. You don't really need both, but I just gave you both. So it says find the length of the arc. The radius is 2, and the angle is pi over 4. If you're more visual and you want to know what you're really doing, you're finding the length of that part in red. Okay, so first thing we need is our formula. Can someone remind me, what's the formula for finding the length of an arc? Chris?
S equals r theta, or size equals arc length equals radius.
So yep, S equals r theta, and now we'll fill in what we know. Well, the question is find the length of the arc. Which letter here represents the length of the arc? Yeah.
S.
S. So we don't know S. Let's leave it. The next thing in the formula is R. What do they tell me R is in this problem? Next. 2. And the last thing I need is theta. Theta is an angle. What's my angle? Yeah, go ahead. Pi over 4. And remember, the angle needs to be in radians. Is pi over 4 in radians? Yeah, it has to be because it doesn't have the circle on it. So it's pi over 4. Okay, so now we just multiply straight across. That's 2 times pi over 4. And what does 2 pi over 4 reduce to? Yeah, that's pi over 2. Now, what did I just find? Yeah? The length of the arc. I just found a length. So that needs a label. In this problem, what label did they use to represent length? This could be different in every problem. Yeah? Inches. So that's pi over 2 inches. What does that mean in inches? Well, it's about 1.57 inches. So S is a length. It would have a label of like inches, feet, centimeters. R is the same thing. That's a length. Theta is an angle. That's in radians. Questions on that? Let's try one more with arc length. So the directions here say find the radius. So we already know. Now I'm solving for R. The arc length is 3 pi feet. And the central angle is 60 degrees. Okay, so Aiden, what's my formula that I'm going to use in this problem? Yep, the arc length formula.
S equals r.
Yep. S equals r times theta. Okay, and let's go through from left to right. The S. Do I know what the S is? What? 3 pi feet. I'll leave feet out of the equation while I'm solving it, but I'll make sure if I need it, I'll put it back at the end. The next one is R. Do I know R? No, that's the question. Find the radius. And do I know theta? Yeah.
60.
Okay, there is an angle of 60 in this problem, yeah. But that's part of it. What do I need to do?
You have to convert
I have to convert it to
radians.
radians. So off to the side, I'm just going to multiply by pi over 180. And what does that 60 change to? Yep.
I was going to say it's pi over 3, but
Yeah. Pi over 3. Yeah. So the 60 is the angle. Just make sure you change it to radians. All right. Now, I've got a fraction next to a variable. It's kind of like if you had something like this. There's a way you can get rid of this fraction by multiplying both sides by something. Does anybody know in this problem what you multiply both sides by that gets rid of pi over 3? It's going to get rid of both at the same time. Yep.
30.
3 is going to be part of it.
3 over pi.
3 over pi. So we're going to multiply by 3 over pi. 3 over pi, that's the reciprocal. That's how you get rid of it. So the pi's are gone. 3's are gone. And the pi's are gone. So what do I get for a radius? Yep.
9 feet.
9, and radius measures length. So that has to be in feet. So this is a circle with a 9-foot radius. Okay. Any questions on that? And that's it for our so angular velocity. Well, velocity means how fast something is going. And angular velocity is used to measure how fast something is spinning. So if you think on like a car, they have a speedometer, but that doesn't measure the speed of something spinning. That measures the speed of an object moving in a straight line. Your speedometer doesn't tell you how many revolutions per minute your tires are making. You could figure that out, but that's not what it tells you. So angular velocity measures the speed of something spinning on a circle. Generally, there are 3 units we use. Revolutions is pretty common. So if you've heard of RPMs, like revolutions per minute, that's the speed of something spinning. You could use like degrees per minute. That's not used as much. And you could also use radians per minute. Degrees, radians, and revolutions are all things that measure movement on a circle. So, why do we need angular velocity? Well, let's look at this circle. I've got 3 different dots that I would like to change the color of. And I want to spin them one time. Okay, and I want you to just watch what happens. So the black, the red, and the blue. Spin them one time. And they're back where they started. Which one of them, well, first of all, did they all travel the same distance? No. Which one of them traveled the farthest? What? The blue dot. And the black one, well, that was right in the middle. It's like it didn't move at all. And the red dot traveled somewhere in the middle. But everybody agrees the blue dot traveled the furthest. Okay? So now, I want you to focus on the amount of time it takes for each dot to go around one time. If you compare the time it took the black, the red, and the blue dot to all go around one time, how do their times compare? Yeah? They're the same. So what does that mean if the time is the same, but the blue dot traveled further than all the other dots? The blue dot traveled further in the same amount of time as everything else. Yep.
Blue dot has a higher angular speed.
Well, the blue dot, if you think about it linearly, is traveling faster because it covered more distance in the same amount of time. That can only mean it's going faster. And that's what gets confusing if we try to measure the speed of these dots, thinking of it in a linear way. Every single dot from the middle to the edge would be going at a different speed if we think about it linearly. But if we think about it in terms of like revolutions per minute, we could say that all these dots make, maybe 50 revolutions every minute. They go around 50 times in a minute. Do they go around different sizes? Yes. But when we talk about RPMs, we don't worry about them. They all went around the exact same amount of time. So angular velocity gives us a way to describe the speed of this whole circle in a simpler way. So we don't have to think of all these dots traveling at different speeds. In general, if you don't see directions on a problem and it says to find the angular speed, the default unit that you use is radians. If the problem says otherwise, find degrees per minute, find revolutions per minute, fine, then do that. But if you do not see a unit, use radians. And what about the time unit? I don't care about the time unit. Use whatever's in the problem. Minutes, seconds, days, hours, whatever's. Now, if we compare that to linear speed, the units are different for that. There's a time unit. Seconds, hours, those are common. But the way we measure distance in a linear way is either feet, inches, centimeters, millimeters, kilometers, things like that. We don't measure linear speed in radians. Radians measures spinning. That's angular. And what we're going to do is we're going to convert between units. That's what this section is about. Converting between different kinds of units. And the way that we're going to convert between units, maybe you've done it like in chemistry or physics, we're going to use what's called dimensional analysis. And it's exactly the same way I've taught you to convert between degrees and radians. If you have a unit you want to cancel out, you put it in the opposite spot, and it cancels. Now, doing it this way does require you to know some conversions. Things I would expect you to know for the test or put on your reference sheet. How many seconds in a minute, minutes in an hour, hours in a day, days in a year. How many inches in a foot, how many feet in a yard, how many feet in a mile, how many feet in a mile? Yeah.
5,280.
Yep, 5,280. That's the one sometimes people don't know. That's pretty much it. Those are all conversions that you would need to know. If it's anything beyond that, like you don't have to know how many pounds in a kilogram. I mean, that's a little harder to remember that kind of stuff. But basic length and time conversions. And what we're going to do is we're just going to start out with a really simple conversion. We're going to convert like days to seconds or seconds to days. One of those two.
Just wanted to mention that the way I memorize how many feet are a mile is using 5 tomatoes, 5280. So
5280.
5 tomatoes,
5 tomatoes.
4 feet in a mile.
Oh.
You have 5 tomatoes, 5280.
Oh, okay. Huh. All right, so let's convert 3 days to minutes. Okay, so if we want to convert days to minutes, we're going to go 1 unit at a time, and we're going to start with the next unit that's smaller than a day. So what is the unit that's smaller than a day? An hour. So we're going to first change days to hours. If you want to think of it like that, it's 3 days. You can always put it over 1. Days is in the top. So I want days to cancel because eventually I want to get minutes. Where would days go in this fraction to cancel? Yep, it's going to go on the bottom. So now we need to write down the conversion between hours and days. What's the conversion between hours and days? Yep.
For every 24 hours, it's 1 day.
There you go. It's a 24 over 1. And now, days is gone, and at this point you have hours. Let's do it again. What's the next unit down from an hour? Yep. A minute, that's our final unit we want. So, first, let's think where hours would go, because we want hours to cancel. Top or bottom? Yep. Bottom. So that means the minutes unit goes in the top. And what's the connection between minutes and hours? Yep.
60 minutes to an hour.
There are 60 minutes in 1 hour. And now you multiply straight across the top and the bottom. The bottom doesn't matter in this case because it's all ones. So we just go straight across the top. 3 times 24 times 60. 24 times 60. 4,320. And that is minutes. No, it's 4,320. Any questions? So that's not speed, that's just time. Let's do one now. That's speed. Speed has 2 units. It has a time unit like we just did, but it also has a distance unit. So now we have 2 units we need to work with. The speed here is 50 feet. That line you could say per second. So we are traveling 50 feet in 1 second. So we're doing 2 problems now. We need to change feet to miles, and we need to change seconds to hours. You can do either one first. Let's deal with feet to miles first. Even if you don't remember how many feet a mile, you should know where feet is going to go to cancel out feet right here. Is it going to go in the top or in the bottom? Bottom. And that means miles is going to go in the top. Now we need to remember it. How many feet in 1 mile? Yeah?
5,280.
5,280 feet in a mile. Now, if you stop there, you have miles per second. Now we want to get seconds to hours. Off the top of my head, I don't know how many seconds in an hour. But let's just go seconds to minutes. Okay, 1 unit at a time. Okay, where would seconds go if we want to get rid of it? Top or bottom? Yep.
Seconds go on top.
Seconds would go on the top. And we're going to go to minutes on the bottom. There are 60 seconds in a minute. Okay, now we have miles per minute. So now we're going to go one more step. We want to change minutes to hours. Where would minutes go? Yep.
Up top?
Up top. Hours would go in the bottom. And there were 60 minutes in an hour. And when you're done, check what you're left with. Miles in the top, hours in the bottom, and that's what they want, miles per hour. Okay, so the way I would type this in, I would multiply everything in the top first. So 50 times 60 times 60. 60. So that's the top. And then divide that by, well, just 5,280. So divided by 5280. Okay, so that's 34.1 miles per hour. You could write MPH, but in this section, that's how they do it. Any question on it? All right, let's try this one. So what we just did here is we converted a linear speed to another linear speed. We went linear to linear. Now we're going to jump between linear and angular. So we have a wheel with a radius of 18 inches, which, just to make that a little simpler, how many feet is 18 inches? Yep.
1.5.
It's exactly 1.5. If you're not sure, you can divide inches by 12, and it changes it to feet. So that's 1.5 feet. I think we need feet later on, so it might help to have that number now. And it's spinning at 1,850. RPM stands for revolutions per minute. That's the common abbreviation for revolutions per minute. No, not anything else. Revolutions. Alright, so they want us to do two things. These two things are totally separate. You don't need to do part A to do part B. So it's like two separate problems. First, they just want us to take the angular speed in revolutions per minute and change that to radians per minute. So let's just practice changing angular speed to angular speed. That part's going to be pretty easy. So let's do part A first. I'm going to move part B if I can. Just move that down. All right, so find the speed in radians per minute. What's the speed they give me right now?
We don't know. Or is it the 1850?
1850, that is a speed. What kind of speed is it?
Revolution.
Revolutions per minute, and that's angular. Angular speed, spinning in a circle. So that's 1,850 revolutions in a minute. Now, they want me to change to radians per minute. So the time unit is okay. We don't have to do anything to minutes. But I need to get rid of revolutions. Even if you don't know the conversion yet, where would revolutions go so it disappears? Yep. That would go in the bottom. And the goal is to get radians, so that would go in the top. Now I need the conversion between radians and revolutions. If you're not sure, try to think of the conversion between degrees and revolutions. If you can think of that, then change degrees to radians. That's your answer. Yep.
Would it be, well, because one revolution is 360 degrees, right?
One revolution is 360 degrees.
Would it be 2 pi to 1 revolution?
One revolution.
Revolution.
Yes. So there are 2 pi radians in one revolution. Because there are 360 degrees in a revolution, and 360 is 2 pi. That's it. You just multiply. So if you want to leave that as an exact answer, we can. What's that, 3,700? No. So it's 3,700 times pi radians per minute. Again, that doesn't really help us to do anything with part B, but that's converting one type of angular velocity to another. Now part B. It says to convert the angular to linear. The idea of angular to linear, the way you could visualize it, is imagine you had a tire on a machine spinning at 1,850 RPMs. And all of a sudden the tire came off the machine and hit the ground and instantly took off. How fast would the tire be going? That's basically what we're figuring it out. So we want to go back to what we started with. You always want to start with revolutions when you're doing something like part B. 1,850. Now, for a time unit in this part, what do they want my time to be? We have minutes right now, but ultimately max. All right, let's get that out of the way. So let's change minutes to seconds. 60 seconds in a minute. Okay, so that quickly that deals with time. And now I want to get rid of revolutions. And I want to get feet. So we don't know the conversion yet, but where would revolutions go so that it disappears? So I can end up with feet. Yep.
On the bottom.
Revolutions would go on the bottom, and feet would go on the top. Now, 60 seconds in a minute, that's a conversion that never changes. 12 inches in a foot, that never changes. How many feet in a revolution? Well, that changes. It depends on the size of the revolution. Is that your revolution? Or is that your revolution? So when you have to convert here, you need to figure this conversion out. Now, if you think about this as a circle, a revolution is really the what of the circle? Yeah, it's the circumference. So if you imagine like that was like a piece of string in a loop, you cut it right there and you flattened it out, and laid it out flat. That's what you're finding. How many feet to go around the circle? One time. That's a revolution. So, formula. To find the length of one revolution of a circle, that's the circumference. And in this case, the circumference is 2 pi r. What was my radius of this circle? Yeah, 1.5 feet. So the circumference in feet is 2 times pi times 1.5. Well, what's 2 times 1.5? Yeah, 3. Times pi is 3 pi. So there are that many feet in one circumference. So this conversion right here is always figured out using the circumference formula. I just need to multiply that up. So what's the answer? Let's see, 1850 times 3 times pi, and then divide by 60. So if this tire was spinning at 1,850 RPMs, fell off the machine, hit the ground, didn't fall over, just hit the ground and took off straight, it would be traveling at 290.6 feet per second. That's easily over 100 miles an hour. So you're probably not going to get out of the way if something's coming at you at 100 miles an hour. So any questions on this idea of converting between units? All right, and the last thing we're going to look at, we're not going to get into it much today, but we'll finish it tomorrow, and you might have to finish it a little bit on Thursday, we'll see, is section 6.2. So we're going to do most of it tomorrow, but there's a few things, if we can write them down today, then we won't have to do it tomorrow. So 6.2 is unit circle trig. First of all, how big is a unit circle? Yeah.
It's a circle with a radius of 1.
Yeah, it's a circle with a radius of 1. So this entire section, we are working with circles that have a radius of 1. So here's a circle with a radius of 1. And this is the whole goal of unit circle trig. First, has anyone done this before? Unit circle trig? All right, so somebody give me an angle. I'd like a nice number, but
90 degrees.
okay, 90 degrees. That's a good one. So 90 degrees. I have my initial side here, and I have my terminal side here. The idea of unit circle trig is that when you draw a 90-degree angle, or any angle, the terminal side is going to hit the circle somewhere. If we made it a little bigger than 90, maybe the terminal side would be over here, and then it would hit right there. The point is, the terminal side hits somewhere, and the whole goal of unit circle trig is to get the coordinate of where the terminal side hits the edge of the circle. That's what you have to figure out. The coordinates for 0, 90, 180, and 270 are actually the easiest ones to find. Because remember, this is the origin. And how big is this circle? What's the radius of it? 1. So to get to 0, 90, 180, and 270, you're just going one unit, either right, up, left, or down. So if this was 90, does anybody think they know what this coordinate would be on the circle? Yep.
0, 1.
That's the coordinate 0, 1. And that is always the coordinate for 90 degrees, and it never changes. How about for 0 degrees? That would be right here. Yep.
1, 0.
That coordinate is 1, 0. And this is 180. Anyone think they know what that coordinate would be? Yeah.
Negative 1, 0.
Negative 1, 0. And what would be the one at the bottom? First, what's the angle that's at the bottom? Yep.
270.
Good. 270. And if I drew a 270 degree angle, the terminal side would be pointing right there. And what would be the coordinate right there? Yeah. 0, negative 1. So those are 4 coordinates that are pretty easy to find the angle for on the circle. Any questions on the idea? So unit circle trig is all about finding the coordinate where the terminal side hits the circle. Now, if you had something like, let's say 45 degrees, well, that's a little harder. This is the terminal side coming up at an angle. It hits right there. There is a coordinate for that, but we're not going to talk about that right now. Okay? Some coordinates are a little harder to find. But we still have to find it somehow. Okay, and I'll show you more about that later. I'm not going to worry about this. This is what I just explained to you. So when we do unit circle trig, we cannot find every coordinate. I'll tell you that right now. You cannot, like if you just named a random angle to me, like 12 degrees, I cannot tell you if I draw a 12-degree angle, it might look like that. I can't give you that coordinate. I don't know what it is. We can only do unit circle trig for certain angles. And when I say certain angles, we can do multiples of 30 and 45. Those are the only angles that we can do on the circle. 12 is not a multiple of 30 or 45.
They have to be a multiple of both or one
Nope.
or the other.
Just one or the other, like 120. That would be doable. But the goal is for any angle that's a multiple of 30 or 45, we can draw it on a circle, and then we can find the coordinate. That's the goal. So what does finding the coordinate do? Well, think about 90 degrees again. Can anyone remember, what was the coordinate for 90? 0, 1. What do you call the first number in a coordinate? Remember, what's the first one called? Yep,
The X.
that's the x value. And what do you call the second number? Yep,
Y.
the y value. If you know these x and y values, we can find what's called the trig functions of 90 degrees. But we need to know these two numbers, the x value for 90 and the y value for 90. So the last thing I'm going to do, we're not going to do an example. I'm going to put up the first three formulas, and we'll do the last three tomorrow. Does anybody know the name of like one of the trig functions? We haven't mentioned them in here yet. Does anybody know the name of any of the trig functions? Yeah?
Sine.
Sine, yep, that's one. Yeah.
Cosine.
Cosine is two. And there's one more that's pretty popular, used a lot. Tangent, that's the three I'm going to give you a formula for right now. Sine, cosine, and tangent. If you want to find the sine, the cosine, or the tangent of 90 degrees, the first thing you need to know is the x and the y value for 90 degrees. And if I asked you specifically about the sine of not just 90, but the sine of anything, you need to take and give me the y value of your coordinate. Do you need the x value for sine? Nope, you don't need it at all. So when we want to find the sine of an angle, we need the y value of its coordinate. When we want to find the cosine of an angle, we need the x value of its coordinate. And if you want to find the tangent of an angle, you need both. You have to take the y value and divide by the x value. So you can see, if you can't figure out the coordinate, you're not going to be able to figure out the x and the y, and you're not going to be able to do any of these formulas. So unit circle trig is all based off knowing a coordinate for an angle. And in parentheses, these are the abbreviations. Usually you don't see tangent written out, T-A-N-G-E-N-T. Usually you see the words T-A-N. There are three other trig functions that I'll show you tomorrow. And they're all very similar formulas to those three. Okay, so we'll talk more about unit circle trig tomorrow. And then, I don't know if we'll finish it tomorrow. We may have to finish it a little bit on Thursday. But the goal would hopefully be to start the quiz in the last half of Thursday I wouldn't quiz you on Thursday if we learn anything new Thursday. That would not be on it. So anything that we do on Thursday, I would save that for the part of the quiz we finish on Friday. And we'll see where we end up tomorrow. Okay, so for tonight, it's just going to be that. Page 335, those 3 questions, that's going to be tomorrow. So all you have to do tonight is page 324. So 56 to 59, 70, and 71. So six questions for tonight.